Okay, hello again. Um, our next speaker is Anna Serafimovic. She'll talk about supply chain assistant. So in many retail chains, stock ordering from stores is being done manually and based on the intuition of the store manager. That creates large problems in supply chain, large stockout and overstock problems. Supply Chain Assistant is an AI product that creates daily sales forecasts and determines optimal stock. Using all available historical data for stock sales and historical weather data with daily weather forecast, the system automatizes the supply process. So, uh, Anna, it's your turn.
Thank you. Hello, everyone. My name is Anna Serafimovic, and I am here today on behalf of ASW Engineering, which is a Belgrade-based IT company that delivers automated software solutions for various businesses. The work that we do is also depicted in the name of the company, whereby ASW stands for Automated Software. So before I start with the presentation, a big shout out to our team lead, Filip Jekic, who actually laid the grounds for this presentation today, but was not able to give the talk because of certain medical problems. In this presentation, I will be telling you about one of our products, the Supply Chain Assistant. But before we dive into that, let's take a step back and notice that the workforce of today is fundamentally changing. The algorithmic workforce is actually emerging with the properties that are fundamentally different to those in traditional workforce. There are a number of companies that operate in algorithmic way, and they have a particular structure which is outlined here. So important decisions are made by a small number of highly trained individuals. Then the business processes are supported by sophisticated automation, which is to say algorithms. And then a huge number of employees are managed algorithmically, and actually they execute tasks that they have received from the AI as opposed to the traditional workforce paradigm where people would give tasks to people. An example of a software supporting the algorithmic workforce is also our supply chain assistant, which I will be presenting to you today. First, let me give you an overall review of our AI platform. So ASW Machine Learning Lab was founded 3 years ago in 2017 in order to answer the challenge of extracting value from data and automating business processes. Our team consists of 7 engineers, some of who also work at the Faculty of Mathematics, University of Belgrade, which is to say that we are successfully bridging the gap between theoretical and applied science. The application of our theoretical knowledge works on top of 20 years of structured data that we have gathered from our clients over the years in a way that I will explain to you shortly. So the result of the 3 years of development is our machine learning platform, which we call Maximus, or ASW Maximus. It consists of a number of mathematical models, machine learning models, optimization algorithms, but in addition to that, the platform provides components that support each phase of a working ML system in production, from data transformations and ETLs all the way to delivering results via web services or via files. A fundamental resource that our ML platform works on top of is data, of course, and data can be structured or unstructured. So the vast majority of the data that we work with is actually structured. It's stored in our databases typically, and it originates from other products of ours, such as ERP, but also from external information systems. But we have found oftentimes that in order to achieve optimal performance, we need to include unstructured data as well that may come from text, images, audio, video, and so on. One important example of unstructured data that I would like to point out here, because it's relevant for what I'm going to talk about, is weather data. So it is common knowledge that weather data has a huge influence on sales. And also there is a study included here on the right-hand side of the slide that supports, scientifically supports what I just said. So we can see from this study that just a few degrees change in temperature can significantly alter the shopping habits of customers, which then influences the final numbers in sales, and ultimately it changes the market demand, and it should also change the supply. So we use a system which gathers weather-related data for certain coordinates that are of interest to us, certain regional coordinates. And the important thing here to say is that we gather historical data when it comes to weather, and we also gather weather forecast. Yes, we also gather weather forecast. So originally, these are unstructured. Sorry for that. I was just looking into the next slide. So originally, the weather data are unstructured, but then we have devised a number of rules according to which they are placed into our databases, where they are basically become structured data, and they are available to be used in our algorithm, as well as in our reporting systems. So the overall architecture of how ASW operates is outlined in the slide here. So the most important part that I want to point out at this time is the ASW Sapiens, which is a very important part in our overall system that is responsible for gathering the data from other data sources that were also built in-house, such as Dominus, which is our ERP system, then Mercantis, we have loyalty. And as well as that, Sapiens also gathers data from external data sources and makes them structured and ready to be used by our ML platform, which is Maximus. So finally, the input data from Sapiens, as well as the predictions and results produced by our ML platform Maximus, are both available to the Tableau server, where they can be visualized and then they can be turned into final products that our customers can use. I would also like to point out here that our AI platform consists of implementations in production that run on either local servers, on big data systems such as Hadoop, and on Amazon AWS cloud. So this slide represents the real course of action from experimental phase to production in our machine learning lab. So first, the part that comes before the navy blue arrow, this one here, represents the initial training on historical data. It is usually a subset of the overall data set. And during this phase, we create an initial model, which we verify the results with whose results we verify with our clients on a subset of the real data. And then after the navy blue arrow, the production part starts. And the important thing to notice here is that changes in data distribution over the course of time, new categories of events, and changes in business processes can influence the performance of an old model that was trained on old data, which is why in production systems, we have developed a retraining system. So, for example, every day or every week or otherwise periodically, the platform receives an increment of data which contains the information about everything that happened since the last retraining. And the model is retrained on that data. And in this way, we ensure that the model remains relevant. It does not deprecate, and it might even improve in performance. So the retrained model is then deployed, and it starts to deliver results. And here we have two main options when it comes to generating results. So results can be gathered periodically and, for example, daily, like in this figure. So either periodically and then sent as results to a database or sent via file transfer, or on other occasions when we need to provide the results in real time, we would opt for web services. Some examples of our successful AI projects that have been developed by our lab are a recommendation system alongside a customer segmentation and clustering system, which was done for a leading loyalty program in the region. Then a price and markdown optimization system, which was also done for a leading retail chain in the region. Then we devised a supply chain assistant, which I am focusing on here. It was for a pharmacy chain. And we also have a couple more listed here, such as chargeback forecast and forecasting the production of renewable electricity sources. So back on the supply chain assistant. Let's say our client is a retail company with 150 stores, and it is wondering how to conduct the supply chain in stores and warehouses. So the main two KPIs, so key performance indicators, that we were focusing on and analyzing here have been stockout and overstock. So stockout, or out of stock event, represents missed sales. So when a product that's in demand is out of stock and people are unable to buy it, we are clearly missing on some profits there. Then overstock is also a major problem because certain products may not be selling very well, but may still be occupying the capital and the warehouse space that could otherwise be better used. So The input data, again, we're going to separate it into the structured and unstructured part. The structured part is what we got from our clients, and those are sales data, where we received information on the quantity, prices, and discounts. Then we received some stock data. We mainly used the quantity of stock in our analysis. And we also received data on how they were conducting their replenishment ordering of products in order to keep the supply chain going. And then the unstructured data that we have not yet implemented, but we plan to include in our model in order to improve the performance, are weather data. We already discussed that weather affects sales greatly. Then local events such as, I don't know, holidays and such. And we may also consider what the competition is doing well and try to incorporate that in our models and give some estimations as to what the certain changes would bring to our client. The algorithms we used is, first of all, gradient boosting, which is the winning one for the time being. It gave us better results on structured data than the neural networks. So it consists of a large number of decision trees, and as we probably all can see, the figure below is actually a representation of a boosting algorithm, and in particular one with decision trees here, where every one of the decision trees trains a model that contains some errors, and then in the training of the next decision tree, the errors are the ones that are given greater weight and sampled more than the rest of the data that was correctly predicted or correctly classified. So back to our problem. Our problem was forecasting sales. In particular, the forecasts were generated every day, and every day we make a forecast for the next week, so for the next 7 days. And the granularity level that we used is item store day triple, which is to say that for every item, we predicted how much of that item is going to be sold in a particular store on a particular day. So our granularity level is that triple item store day. This is example of one of the results that we received using this model. So the blue line represents the ground truth, so what really happened in sales. Then the very close to the blue line, there is a orange line, which represents our forecast for sales. And then the red line is the real situation when it comes to stock quantity. So we can see here, so this is just like a summary for all stores, for all products for the time being. But it still says that our predictions are pretty good here. Then this result represents the red line underneath is the stock quantity, and the green line above it is the stock forecast. So when we have products that are going out of stock, this is the prediction that says if the stock were this much, then we would not be facing stockout events like that. So this is a probabilistic forecast for determining optimal stock, which I also talked about here in the previous slide. So we have gained knowledge on optimal, minimal, and maximal stock quantity. So the red line that's in between the confidence interval represents the trend in the real data. Then the green line, the red line that is not smooth but wiggly is our prediction for sales. And then the confidence interval is what we took as a prediction for stock. To be more precise, the upper bound of this image is what we indicated as our stock forecast, as our stock recommendation, just like in the slide before. I mean, this is actually the picture. This is the insert from the confidence interval. These two are talking about the same thing. Then let's just get back to the KPIs once more. We were optimizing stockout, the number of stockout events and the number of overstock events. Stockout event happens when an item is out of stock, so the quantity is 0 in supply, but there has been a great demand for the item while it was in stock. And then the overstock event, once more, is the event where we have more of the item in stock than is predicted to be sold next week. That's the precise definition. And when trying to optimize the stock, supply, and demand chain, we have considered stock replenishment, so buying of new stock for the warehouses, then the selling of the existing stock, as well as stock transfer between the warehouses. If an item would be more needed in another location, then we would recommend that it should be moved to another warehouse. And this is the first dashboard that represents our results. So in the upper right-hand side corner here, we can choose certain filters, such as, for example, which key performance indicator we are going to look at. Here, stockout was selected, and therefore we have the ground truth versus the forecast of the stockout on this graph here. Then we could choose the organizational units, or in other words, the stores. We could choose minimum sale, because we might not want to look at certain items that are not even being sold. And we can choose the time period. The time period that was selected here is indicated under the title, and it's 1st of September 2020 to 14th October 2020. So we have the overall number of stockout events, how much we lost monetarily due to those stockout events, as well as what the prediction said about those events. Then down here on the left-hand side, in the lower left-hand side corner, we have a table with a drill down of these numbers that are now available to us per item. So basically, this number 8,971, which appears here as well, up here, is basically the sum of all these, and similarly for the rest. And on the lower right-hand side corner, in the lower right-hand side corner, we have a map, and it represents what it represents. It's clear what it represents. So if we click on this replenishment button, we would go to another dashboard, which deals with stock replenishment. This is also like a summary for all stores, for all products throughout time. And we considered that it was important for people to see how much it was going to cost them to refill the stock according to our recommendations. And then when we click on Create Grid, we would come to the best part of this product, our pride and joy. So the stock replenishment grid, which actually tells us by product, which are here in rows, and by product by organizational unit or store, which are the columns. So how much do we need when it comes to replenishment of this product, and how much it is going to cost us? And then the red ones are particularly indicated the products that have suffered stockout events, out of stock events, but we also have the same piece of information for them. So for instance, this product 54544 in this store 29992 needs to be replenished by 13 items, and this is going to cost 4,151 something. It's not dollars. And in conclusion, the use of the supply assistant improves those two KPI values. And we have estimated that the stockout was reduced by about 80%, while the overstock was reduced by 50%. And if there is anybody who is interested in a further demonstration of the product, you can write down the email address. I'm sure that the slides will be distributed as well.